Okay, hello everybody. Welcome to the web security session today of PAM. So we have three great papers lined up for today, covering aspects ranging from domain squatting to block lists to the use of outdated software in web stacks. So before we start, I just wanted to do a bit of housekeeping. As usual, we'll have an active Slack channel, which is hashtag PAM2021 session 5 web security. If you've not joined it already, please do so. The link is on the website, as I'll be asking you to use that for the Q&A. Also, quick reminder, the session will be recorded. So if you do not want to appear, feel free to write any questions to the Slack and I can read them out on your behalf. So our first talk today is going to be by Yue. So Yue is a PhD student from the University of the Chinese Academy of Sciences. He's now a security researcher currently interning at ByteDance, and his main research interests lie in the area of network security. So without much delay, let's please go with the first presentation.
Hello everyone, my name is Yue Zheng from UCAS. The topic of my report today is about the malicious redirection in squatting domain names. Before introducing our work, we look at a sample at first. The user first queries a combo squatting domain of Nike. Then he is redirected to the second URL via HTTP. Next, he suffers 3 JavaScript redirections and landed on the page A. There's a loading bar and a button on this page. If the user has not clicked the button before the bar is loaded, he will be auto-redirected to the page B, and then redirected to the final malicious site C in the same way. In our traditional view, only the last 2 sites are actually displaying illegal contents, while the parent nodes are just acting as the relay nodes. So, except to the last 2 sites, this sample has 2 main parts, the start squatting domains and the relay nodes. So, what is domain squatting? Domain squatting refers to the malicious registration of domains that are similar with the well-known brands. There are many squatting types, such as tempo squatting and combo squatting. Another part is the URL redirection, which has 3 types, namely the HTTP-based, JavaScript-based, and the HTML-based. This slide shows the basic model of malicious redirection. In the traditional delivery mode, the client faces the compromised site directly. Just like the left page, the attacker shows illegal content on the site W, and the client faces its contents directly. But this mode also makes the compromised site to be taken down very easily. So the attacker adds several barriers before the compromised site to enhance its safety. Just like the right page, the attacker adds 2 nodes before the site to verify the identity of the client, such as its geolocation or its IP address. So, why the attacker leverages both domain squatting and redirection? By leveraging redirection, the attacker could verify the identity of the coming traffic and assign the user with different destinations. This relay nodes indeed improve the concealment of the final site, but they also lower its accessibility. So the attacker employs squatting domains as his traffic entrance. To monitor such redirections, we selected more than 2,000 brands from both Alex list and CN list, and searched their squatting domains in our PDS database. Then we crafted a headless crawler to query these domains and load the requested resources. Our labeling result shows that more than 27,000 squatting domains are abused to deliver illegal contents. So, based on the collected performance logs, we recovered the redirection tree of each sample. We found that More than 70% of the malicious symbols conduct URL redirection, and more than 4% of them conduct at least 10 redirections in one chain. Besides, there are several malicious symbols perform an astonishing 26 times of redirection and finally landed on the same illegal fundraising site. This slide shows the redirection type of malicious symbols. In this histogram, OScript indicates the JavaScript code imported from outer files, and IScript indicates the JavaScript code that hard-coded inside the script tag. We can see that about 35% of the malicious symbols employ JavaScript code to conduct redirection, while this number is only 2% in benign symbols. Besides, there are 28% of the malicious symbols covering an oversized iframe on the final page. This slide further introduces the hard-coded JavaScript-based redirections. This script fills in the hyperreference of the A tag and emulates the most click event to achieve the redirection goal. Now is the imported JavaScript-based redirection. The script tag imports the redirection code from a file called common.js. There's only one line code in that file, and all its key fields have been hex encoded. Further, we measured the domains that acting as relay nodes in the malicious redirections, and we found that the sharing phenomenon is very common in our symbols. For example, about 5% of the URLs were reused by more than half of the malicious symbols, and about 10% of the second-level domains were reused by more than 60% of the symbols. Besides, like the table showing at the bottom, the sharing also reflects in the internet infrastructures, such as the IP and the AS number of the web server. Now is the conclusion. We give the first insight into the malicious redirections that start with squatting domain names. Besides, we employ the performance log to rebuild the redirection path. It is much more convenient than the traffic-based recovery methods. Our investigation also reveals that attackers prefer to leverage the imported JS code and the iframes to perform redirections, and the resource sharing is very common in this activity. So that's all for my report. Thank you very much.
Fantastic stuff. So we have UA on the call right now. So if you'd like to unmute yourself, and I'll hand over to the floor. Does anybody have any questions? You can pop your indication of a question into the Slack channel, and we can unmute you. Okay, so maybe I can kick off with a question. So I was curious, you did a breakdown of what was triggering these redirections and talking about how it was triggered mostly by JavaScript or HTML. Do you know what was it actually injecting these redirections? Was it the person operating the website, or do you suspect that these machines may have been, for example, infected, or potentially intermediate middle boxes were interfering with the traffic? UA, you're muted.
Okay, can you hear me?
Yes, we can hear you now. Great.
Okay, can you speak much slower? I can follow you.
Yes, I was just curious. When you see these types of malicious redirections, do you suspect that the websites themselves are creating these chains? Or do you suspect that there might be a third malicious party responsible? That might be, for instance, some malicious adverts that have been hosted on the page, or alternatively, it might be the fact that the web server has been compromised in some fashion.
The relay nodes has in my study, there are two kinds of relay nodes. The first one is just like a web server. They are acting as a relay nodes to do the HTTP transfer. And the second is iframe. The attackers put some iframe tags in the page, and they displayed some illegal contents in the iframe.
And for instance, were those iframes you think operated by third parties? So for example, is it advertisement content in there which is triggering redirects?
Sorry, I really can't follow you.
So I was just curious if the entity responsible for initiating those redirects is the first party page, or do you think it's being triggered by a third party that's hosted on the web page?
The page are not compromised, and in my study, this page are almost the gambling site and all adult site, and they are not acting as such as a phishing site. So the owner of the site do the redirection by themselves.
Okay, it's interesting. Okay, so let's hand actually back to the floor. Do we have any other questions from people? Again, please feel free to pop your indication to want to ask a question in the Slack channel, session 5, web security. Okay, well, it seems like we don't have any other questions coming from the floor. So let's thank our speaker, Yue. Thank you very much for the interesting presentation. And we can move on to the next presentation slot. So the next presentation slot is going to be delivered by Nurala. Nurala is a PhD student at the Institute for Internet Security based in Aachen in Germany. And the research interests center on web and artificial intelligence security. So without any delay, I will hand over to the video.
Hi, my name is Nurullah Demir. I am PhD student at Institute for Internet Security in Germany. I will today present our study and its results that we worked on together with Tobias Urban, Kevin Wittek, and Norbert Pollmann. Today, we have a pretty complex web environment that consists of a variety of different technologies. On the client side, we have JavaScript libraries, frameworks, and on the server side, programming languages, web servers, databases, and many other third parties. So it's really not easy to keep a web environment secure because of its variety. And any security vulnerability in a component in the chain can endanger the whole system. So at that point, processing updates, adopting new releases is very important to keep this environment secure because security vulnerabilities are being fixed in new releases. And in our study, we wanted to assess the update behavior of websites, measure if they use outdated software, and test the security implications of using outdated software. And for that, we conduct a large-scale analysis on 5.6 million websites. For our measurement, we used different data sources. We collected historical data of crawled websites from HTTP archive over a period of 18 months. That includes the data of the crawl, the list of visited origins, and identified software products with their version on websites. To determine if a software is outdated or not, we need the release history of each software. For each software provided by HTTP archive, we identified its release channel. In most cases, this was GitHub. We collected all releases for each software via GitHub API, and for software that are not present in GitHub and have their own release channel, we collected the release history from their official web pages manually. And to identify the vulnerabilities on web pages, we collected the vulnerability database provided by NVD. To enrich our dataset to make it more reliable, we have taken some steps like we converted all versions from these data sources to a standard, to a server format, and we also dropped all noises that we could identify. So we correlated and mapped all data together. So finally, we know now at each measurement point if a website runs outdated software or not, and also know if there are any known vulnerabilities for any used software. After bringing all data together, we had a total of 5.6 million distinct sites and about 32,000 releases and more than 114,000 vulnerabilities. So our results to the update behavior of websites, we had a median of 3 evaluable software products per website, and our measurement showed that 94% of all observed websites were not fully updated, which means these websites run at least one outdated software. And on average, 74% of used software in a web page were outdated. The average age of utilized software was almost 4 years old. And we find also that on average, there were 41 new releases for outdated software. And generally, we see that client-side software are older than server-side software. For example, here, JavaScript libraries and frameworks are older than programming languages like PHP and web frameworks and web servers. In our dataset, we saw that server-side software has a shorter release cycle, which may be one of the reasons for the differences. To get a better understanding of the update behavior of websites, we observe now the adoption of releases. We record that each month there is a new release for 67% of software, and each month only 7% of websites process any update on their website. And the mean time between 2 updates on a website is 5.6 months. And we also found that the patch releases are processed most frequently. Here, e-commerce software, content management systems, JavaScript libraries, programming languages processes the patch releases most frequently. So here we see the threats that result from the usage of outdated software. 94% of websites have at least one vulnerable software, which was slightly increasing over the course of our measurement. And our measurement for the last point shows that 12% of websites run at least one software with a very critical vulnerability. And we see that performing updates has a significant impact on security. On average, severity of vulnerabilities is lowered from 6.2 to 2.4 after performing updates. And we found that less popular websites are affected by more severe vulnerabilities. And the good news today is that the severity of vulnerabilities is decreasing over the time, which we can see here. So to summarize, we tried to highlight the current state of the web by evaluating update behavior on web pages, and we showed that most of utilized software is outdated by even more than 4 years. and also showed that 95% of websites run software with known vulnerability. Our study must be seen at that point as an upper bound because using a product with known vulnerability doesn't automatically mean that it can be exploited. For example, it's the case if the vulnerable module of the product is deactivated. Nevertheless, our study highlights still that website providers need to take care about their update processes. Thank you very much for the listening.
Fantastic stuff. Okay, so Nirala, if you can unmute your microphone. I think we have a question from Oliver. So Oliver, please feel free to unmute and ask your question.
So thanks for the really nice talk. So one of the things that I was wondering is that you looked into a couple of software packages that were used by those websites. Are there any insights on which of the ones were the most concerning in terms of like being the least updated by the site administrators? So which was the software that the administrators were the most sloppy about, if you want to say so? And in general terms, like what guidelines would you distill out of this that you would give to website providers?
Yeah, thank you for the question. That's a great question. But our main data, we use the HTTP archive dataset. So we really don't know if an update is processed or performed by a website administrator or by a hosting provider. This information, we don't have it. So it's maybe it's a question for future work, but we had unfortunately no information about if an update is processed by a hosting provider or website operator. So
okay, cool. Thank you.
yeah.
Do we have any other questions from the floor? Okay, so whilst people pop their questions to the Slack, I'll take the chair's prerogative and maybe follow up a little bit on what Oliver said. I was curious if you tried to correlate your findings with any other best practice that you can observe on these websites, such as appropriate use of cookies or cookie banners, open privacy statements, and so forth. And if not, did you find any correlations with other factors, such as the types of websites?
Yeah, the types, you mean the type of the website, like if it's a business web pages or banking web pages?
Exactly, business, shopping, video, social media, so forth.
Yeah, we actually wanted to use such a data set, but we didn't include that in our study. So we have also no information about that, and we didn't analyze how the results change based on websites type. We could actually integrate such a data set by using external data set, but we didn't do that, and it was out of scope for our study.
And did you spot any trends, as I mentioned, with other best practices? So, for example, do operators who maintain up-to-date software also do some other things on their websites, which we could consider best practice, like having appropriate cookie banners?
I didn't understand your question.
So I was just curious if those websites that do maintain up-to-date software also follow other best practices in web administration.
Yeah, you mean like if they use security HTTP headers or something like that?
For instance, yes, so correlating with use of secure.
Yeah, we didn't run an analysis about that. We just checked if they perform or deploy the new releases in their environment, and we also didn't check any other features if they use any certificate or any other security mechanism. We didn't also check it.
Interesting. Do we have any other questions from the floor? Please feel free to pop them into the Slack, or just a quick announcement to say you'd like to ask a question. I'm sure there must be some burning thoughts in people's minds. So actually, whilst people just do that, I did have one other quick question, nitty-gritty question. how did you actually go about identifying the versions across all these different pieces of software? Because this can be notoriously difficult, because even with a small reconfiguration by the administrator, the information could be represented in a totally different fashion.
Yeah, that was really a hard work for us, because we had totally more than 300 software products provided by HTTP Archive, and we had to really identify for each software their release channel, and it was really hard to find the release channel, and mostly they were actually on GitHub, but it wasn't enough also to identify their release channel on GitHub, because on a repository, a provider can publish more than one product in one project, and so we had also to filter, like if the software provider used the same channel to also publish their other softwares. It was, for example, it was the case if a plugin or add-on was also used in the same tags in GitHub, and we had to write for almost all products regular expressions to exclude such of releases, and we had to run this task manually, and it was hard work for us. Yeah, but we found the release channel so manually, and since HTTP Archive uses Webalizer as extension in their crawler, and the data is actually provided by Webalizer's extension, and they also don't have such information.
Mm-hmm. There's basically a lot of manual heavy lifting. Yeah. The obvious follow-up question would be, how confident are you that you captured all these different versions? Did anything slip through the net, do you think?
We have any question?
So I was just curious, how confident are you therefore that you actually wrote regular expressions that capture all the different variations that you might be looking for?
So we had normally, for example, for PHP they have more than 5-6 tags for a product, and we really checked all. We checked the main software product, which was provided by HTTP Archive. We found it, and it was almost the same prefix, or that's why we could exclude it with our regular expressions. And it wasn't always the case, but we had to exclude the prefixes and to convert our versions to a standard semantic version.
Mm-hmm. Interesting. And I think, Oliver, if you'd like to unmute, had a quick follow-up question on that.
I think you partially answered my question. So the question was the software versions that you're getting. It's kind of user-provided input, and as security researchers, we know that we shouldn't take user-provided input for granted. So what kind of sanity checking did you do on top of that? E.g., for example, checking if the software version that is claimed to be running on that on that web server was not released after the actual measurement time, and like these kind of just sanity checks.
Yeah, that's a good question. We had such cases, and we identified that, for example, we also saw our data set, for example, WordPress 8, which is actually not now on the market. We compared the release date of the software products and identified software versions. We compared them and excluded the records if they were false, and if even the software version not on the market before the release. I mean, we checked it and we excluded the versions.
Okay, cool. Thanks.
Cool. So I think that brings us roughly to the end of the Q&A time slot. So let's thank Nirala again for the interesting talk.
Thank you very much.
I'm sure he'll be online Slack if you have any follow-up questions. And let us move to the next talk, and in fact, the final talk of this session. So this is going to be delivered by Vector, who is a PhD student based at UC San Diego and advised by Kirill Levchenko and Stefan Savage. So Vector's recently graduated and is actually currently working at Google as a software engineer. So without any delay, I'll hand over to the video.
Vector. Today I'm going to present our work, Clairvoyance in Foreign Blocklist Use on the Internet. This is a joint work between UC San Diego and the UIUC. So what is blocklist? A blocklist is a list of indicators that are known sources of malicious activities, like IP addresses or domains of command control servers, botnets, or senders of spam emails. They are widely used in all kinds of security products like firewall or SIEM to directly block traffic or generate secure alerts for people to investigate. There are many public and commercial providers offering this data. Here I give some examples of public and commercial providers. And this is a thriving industry with market size predicted to surpass $13 billion in 2025. So with this many providers and all the attentions, there's one particular question that there's little people have looked into before in our community, which is how people are actually using this data. This is important because it's not only help us understand adoption of the data, but also give us a sense of the potential impact this data can have on the internet. And this is a problem this paper tried to look into. There are many ways people can use blocklist. So in this study, we focus on one particular use case, IP-based traffic blocking using IP blocklists, where people proactively block incoming traffic if the source IP matches the data in a blocklist. And this blocking is on the network layer. In this paper, we propose, implement, and test a technique for inferring the deployment of such blocking behavior. And we conduct a pilot study to measure the popularity of such use cases. So first, how do we infer this blocking in the first place? We do not have access to IPs on blacklist. Either do we have access to the target hosts we want to measure. So how do we, from a third measurement machine, measure if a target host blocks an IP in a block list? So that requires side channel. So here we use an old technique, IPID side channel. IPID is a 16-bit field in the IP packet header. It is used in IP packet fragmentation and reassembly. And as you can see, they need to be unique throughout a communication. And many old operating systems use a shared monotonically increasing counter to implement this feature. And this side channel gave us opportunity to measure the blocking. So for target host, we first send a probe packet to get the first IP ID, let's say 3. And this will trigger the IP ID to +1, now it's 4. And then we send another packet, but we spoof the source IP address to be an IP on a block list. And if there is a blocking in place, the target host will not get this packet and the IP ID will not change. So if we probe again, we will see the IP ID now equals to 4, just +1. On the contrary, if there is no blocking in place, then on the second stage, the target host will get our spoofed packets, triggering the IP ID to further +1. So then our later probe will get the IP ID equals to 5. So now there's a gap. So the difference between these two scenarios will help us to distinguish that the target host is blocking the IP on the block list or not. And this is how this technique works on a high level. Of course, to make it work in real world, we need to take into consideration all kinds of noises. I will not go into the implementation details, and you can find that in our paper. And with the technique set, you can see that this will only work on certain type of hosts. We refer the hosts that are suitable for this technique as reflectors. And there are 4 criteria. Shared IP/IT counter, which is the side channel, low traffic, no ingress filtering, and no stateful firewall. And to test if a reflector is blocking traffic based on a particular IP block list, we sample IP from that list to test. And the sampling also need to meet certain criteria. I will not go into these criteria in detail, but all these criteria are here to ensure we will have as little noise as possible during our measurement. So with that said, now we will present our evaluation. We evaluate our technique with a pilot study where we scan online hosts in the United States to find suitable reflectors. And then we run a quick test over 100 IP blacklists to choose the most blocked ones for our in-depth pilot study. In the end, we select over 200,000 reflectors and 9 block lists for our pilot study. In each block list, we sample 25 IPs and test these IPs against all the reflectors. We repeat this experiment 3 times and conclude a reflector is using a block list only if it blocks all IPs we sampled from that list. So here is an overview of our measurement result. In total, we discover 1.9% over 4,000 reflectors are using a particular block list. And there are another 21% that block some of the IP we sampled, but not all of them. The rest do not show any blocking behavior. So looking into that 1.9%, here's a breakdown of all the reflectors that are using each of the block lists. And as you can see, the most used block lists are Spamhaus drop and Spamhaus e-drop. We also look into the pairwise intersection and organization breakdown of all the reflectors that uses certain block lists. And there's some interesting results you can find in our paper. Besides that 1.9%, there's still a significant percent of reflectors that block part of the IPs we sampled in each block list, but not all, as we can see from the graph. This suggests that many reflectors deploy some blocking policies that overlap with those block lists we choose. In conclusion, we proposed, implemented, and tested a technique for enforcing the deployment of IP-based traffic blocking using block lists. Our pilot study covered over 200,000 US hosts, identified block list usage in 1.9% of these hosts, and found blocking behavior in roughly 1/4 of all hosts. And although this technique only works in certain hosts, it actually can be extended to work on a broader set of machines with the latest operating system, using advanced IP-ID inference technique demonstrated by a recent Usenix security paper. And the future study should continue looking at this problem and get a clear picture of the block list usage on the internet. Thank you very much.
Great stuff. So I'll ask Vector to unmute his microphone, and if anybody on the floor has a question, please feel free to dive into the Slack channel and share it there. I think Lars is actually typing, so if Lars would just like to unmute his microphone, you'd be welcome to just speak out loud your question. Okay, so whilst we wait for Lars, I also noticed that Oliver's typing. So Oliver, if you'd like to just unmute, you're welcome to ask a question directly.
So thanks. One of the questions that I was wondering about is how did you actually select the block lists that you used for the evaluation? So there's a large set of them available. Some of them are free, some of them are commercial. So the free ones are obviously easier to use. The commercial ones you sometimes have to pay for, so they're a little bit harder to access as researchers, but then they have a large footprint in the corporate world. So how did you go about actually selecting the block lists that you were using?
Yeah, can you hear me? Yep. Okay. So that's actually a good question. We do not have access to those commercial lists. So all the lists we tested are public blacklists. We have a repository of over 100 public IP block lists, as I said in the talk. And we run a quick test to select the top 9 IP block lists for the in-depth pilot study. And I do acknowledge your concern that the commercial ones, which we do not have access, might have a big footprint. However, based on our previous experience, we do find that commercial block lists are often incorporate data from public IP block lists. Some high profile ones like Spamhaus, Drop, eDrop, and also some abuse.ch malware C2 list are often incorporated into the commercial ones. And I think that somehow explain the findings that we see like over 20% of the hosts that show some blocking behavior that partially overlap with the IP we sample from the block list, but not all. Yeah.
Thank you. That makes a lot of sense to me.
Great. And Oliver, I think you have a question.
Yes, thanks for the great talk. I was wondering whether you basically made sure, basically you're using spoofed IP packets, right? So did you ensure that those were not blocked at the upstream for upstreams or ASs which do filtering based on the source IP address?
Yes. So in the talk, due to the time limitation, I basically just skimmed through that. I mentioned that to be able to use as a reflector in our study, the hosts need to meet certain criteria, and one of them is no ingress filtering.
Yeah.
Which is the host should not be able to detect the packet is IP is spoofed. And to select the hosts that meet this criteria, we test vigorously from 7 different geolocations around the world. And sending spoof packets to all the hosts with a source IP that we own. So then we say if we receive the responding from those hosts on the IP we own, then we know they are not dropping those packets.
That's great, thanks.
Yeah, that's how we select them.
Cool. And Lars has a quick question, which I'm going to read out on his behalf. So he wonders, maybe it's possible that the hosts are using mirrors of the block list, and these mirrors are lagging behind for some amount of time, and that's why they don't necessarily perfectly match the versions you have. So I suppose a broader question is, at what point in time did you collect those block lists, and how did you ensure that they mirrored when the block lists were installed by the administrators?
Excellent question. We did take into consideration of that. So in one of the criterias I mentioned when selecting IPs in block list to test, we actually only select the stable IPs, meaning that they have been in the list for at least 2 weeks before our test. So this 2 weeks is of course an ad hoc choice, but it's just to ensure that at least this IP has been stay in the list unchanged for 2 weeks. So, I mean, if you are lacking for 2 weeks, otherwise we will probably catch you. But that lacking is definitely one potential source of noise. And if somebody will just incorporate an IP block list and never change it after they first install it, and that might also contribute to the partial blocking we observed.
Cool. And we have a thank you in the Slack channel. So whilst we wait for any other questions to drip through onto the Slack channel, I had a quick question. Did you check at all the consistency of these block lists when used across a network or autonomous system? Because what we've seen in previous studies is if you take 2 hosts within a single autonomous system, or even a single /24, and do the same measurements from them, particularly involving things like middle boxes, you might get wildly different results. So did you check that consistency, and were you confident that you weren't overgeneralizing when you observed perhaps one host seeing some blocks?
Yeah, excellent question. We do check the consistency, and you can find more results. Is actually, I have a link in the paper linking to my dissertation where I have a more in-depth result of the consistency analysis. So basically, what we did is we check if the blocking behavior is consistent among IPs within the same /24, because autonomous system might be too big a granularity. So we heuristically use /24 for our consistency analysis. And we found that most of the time they are consistent, but there's still a significant percent of the cases that they are not consistent, meaning that the IPs in the same /24 are not blocking the same set of IPs we sampled from a block list.
Yeah, and I'd hazard a guess that that's being caused by things like firewalls running on people's local machines.
Yeah.
Yeah, that's what I thought. Wonderful. Okay, we're actually bringing us to the end of the session perfectly on time. Thank you, Vector. That was great. I don't think there are any final questions in the Slack channel, but obviously people are very welcome to follow up offline. So we now have a 15-minute coffee break, so people can go freshen up, and we'll be back on the call with the DOS session chaired by Brad. So with that, I'll say thank you to all the speakers. Thank you to those people who asked the questions, and enjoy the rest of today's